Here we have Riemann integration approximating sign between 0 and 2 pi. Riemann approximates the area under the curve as some negative decimal less than 1/100th. So why would we want to use another approximation method such as Monte Carlo integration? Look at those overlapping boxes and missing spaces. The area is wrong. But law of large numbers says it will converge to actual value when numbers of boxes goes to infinity, which is also true for Riemann. But consider higher dimensions. As space increases, the probability that hyperrectangles overlap decreases, and the computational cost of Riemann increases. When this happens, Monte Carlo integration is much more advantageous than Riemann integration. We could uniformly space out our multidimensional hyperrectangles. Since Riemann is deterministic, we will get the same calculation every time. If we instead randomly generate our hyperrectangles, we now have different numbers we can add together and take the average of that sum. That is, we can apply central limit theorem. Central limit theorem also applies to sum, since sum divided by size, which is a constant, equals average. Also notice that the Monte Carlo integration inherits variance from a sample space. We can compare this to k nearest neighbors performance. Suppose points are uniformly distributed in a p-dimensional hypercube. If we want to construct a sub-hypercube to capture a fraction r observations, what length I should be used? We use the equation I equals r to the power of 1 over p. Uniform data points sparsely fill multidimensional space. Your nearest neighbor is super far away.